Hi, welcome to Lecture Online. Today we shall be solving numerical solution to ordinary differential equation using the Taylor series method. So in this video, I'll be taking it step by step in order to solve a numerical problem of differential equations using the Taylor series method. So I will be using this example in the board that dy dx is equals to 1 all over x squared plus y at initial condition y of 4 is equals to 4 in order to find y of 4 and y of 4.2. So in order to solve this problem, there are some steps that we need to take in order to find the solution to this particular problem. First, we need to know the general expression of the Taylor series. So by then we will obtain a general solution using the condition given to us so that we'll be able to find y of 4 and y of 4.2. So I want you to sit back tight and follow step-by-step method in order to solve this problem. Please don't forget to like this video, share, and subscribe to my YouTube channel. Thank you. Right, like I said previously, this is the expression in order to solve any numerical problem using the Taylor series. So this expression is the general solution to the Taylor series. Please don't forget this continues on and on and on to the last derivative at which we have been asked to find. So in this video, first what we will do is order to find the derivative y prime of x naught, y prime prime of x naught, and y prime 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 of x naught. Then we are going to put it into this equation so that we can obtain the general solution in order to find any other problem that is attached to the question, meaning that we can easily find y of 4 if we have obtained the general solution and y of 4.2. So I want you to sit back and relax while we find the solution to this problem. Thank you. Right. So the question given by dy dx is equals to 1 all over x squared plus y at this initial condition. So I want you to note that y of 4 equals to 4 you can be compared with y of x is equals to 4, meaning that y is equals to 4 and x is equals to 4. So our initial conditions are y naught is equals to 4 and our x naught is equals to 4. Don't forget, I said we are going to find y prime of x naught, y prime prime of x naught, and y prime 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 of x naught. Then we substitute it back to the general expression. So from our elementary mathematics, we know that dy dx is the same thing as taking the derivative of y with respect to x, meaning that from this question, we can say that y prime is equal to 1 all over x squared plus y. Yeah, dy dx is the same thing as y prime. Taking the derivative of y with respect to x is the same thing as this expression. But don't forget, with this initial condition, we need to slot this initial condition in order to get our y prime. Now, our y prime of x naught is a numerical solution. Numerical solution, meaning that the value is going to be a number. So, y prime of x naught is equal to 1 all over x naught squared plus y naught. So putting our initial condition into this, we are going to have y prime of x naught is equals to 1 all over x naught is given to us as 4 squared plus y naught is given to us as 4. So we have 1 all over 20, which is 0.05. Now, in order to obtain our y prime prime of x naught, what we have to do is to take the derivative of this function again, because if we take this derivative again, we obtain this, then we insert our initial conditions, then we obtain another numerical value. So, and if you check this problem, is that of a quotient rule. Quotient rule is a division, something all over something, and the derivative is with respect to x, but y is attached to it, so this differentiation will be done implicitly. So I call this top, I call this bottom. Now it is, the formula is bottom d top minus top d bottom all over bottom square. So when I mean d top, I mean differentiate the top. When I mean d bottom, I mean differentiate the bottom. So we're going to use this technique in order to differentiate this problem implicitly. So y prime prime is equal to, the bottom is x squared plus y. D bottom, meaning multiply the bottom with the top. Bottom, d top, differentiate the top, and the top is a constant, and the derivative of a constant is 0 minus top 1. The bottom means differentiate the bottom. So if I'm differentiating x and y, I'm going to do that implicitly, like I've said. So the derivative of x squared is 2x plus the derivative of y becomes y prime all over bottom square. Bottom, x squared plus y all squared. So the multiplication of any function with 0 is 0, meaning 2 times 0 is 0. So here becomes 0. So y prime prime will be left with minus 1 into 2x plus y prime, close bracket, all over. You distribute this power to the expression inside, it becomes x to the power 4 plus y squared. So if we insert everything, values given to us, y prime is 0.05, x is our x naught, y is our y naught. So if we do that, we are going to have minus 1 into 2 into 4 plus 0.05 all over 4 to the power of 4 plus 4 to the power of 2. Right, so quickly, when you insert this using your calculator, here we're going to have this multiply this plus this, we're going to obtain minus 8.05 all over 4 to the power of 4 will give us 256 plus 4 to the power of 2 is 16. So if you divide this by, okay, we need to add this minus 8.05 all over 256 plus 16, we are going to obtain 272. So when we divide this and this, we will now find out, we have, see please, from here we have already inserted our initial condition. So here is equals to y prime prime of x naught, because we have inserted the condition. So that's why it's looking like this. So y prime prime of x naught becomes, we have that minus 8.05 divided by 272. Our result will be given as minus 0.029596 approximately. Right, in order to obtain the third derivative from that expression, we have to differentiate this problem, this particular equation, once more, then we'll obtain the third derivative. So the third derivative, y prime prime prime, is equal to bottom. Don't forget, bottom, when I said bottom, we write the expression below, which is x to the power 4 plus y squared, multiplied by d top. So I'm going to differentiate the top. Differentiating the top implicitly, I'm going to have minus 2 plus y prime prime. You close it, the bracket, minus, don't forget, bottom the top minus top, so minus 2x plus y prime. Sorry, I have to erase this problem. I need to erase this so that I can have space. Bottom the top, differentiate the top, minus top the bottom, mean differentiate the bottom. If I differentiate the bottom, we are going to have 4x cubed plus, now differentiating y squared implicitly, I will obtain 2y y prime implicitly, then all over bottom square. The bottom, I'll just square it, square the bottom. So this is the third derivative of our problem. Next is to find y prime 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 of x naught. Don't forget, our x naught is 4 and our y naught is equal to 4. And also we have obtained that our y prime of x naught is 0.05 and our y prime prime of x naught is minus 0.029, and so therefore. So we are going to impute those into this particular solution. So sit tight while we do the substitution. Please make sure if you are doing this, you are substituting correctly in order to have the correct answer. So we are going to do the substitution in the next 1 minute. Right. So y prime prime of x naught will give us this solution. So if we further simplify this problem, we are going to obtain the following result. Right, I want to make a little correction. The sign here initially I wrote positive, but it's negative. So by the time we expand this particular problem, we insert the value of x naught and y naught and y prime prime into the expression that was written for y prime prime. We are going to obtain that y prime prime of x naught to be 0.023226. So now we have gotten all what we need. We have our y prime of x naught, we have gotten our y prime prime of x naught, and we have gotten our y prime prime of x naught. So we're going to insert it into the general equation using the Taylor series method. So I'm going to do that while you follow me, and make sure you are doing it yourself so that you could understand better. Right. We have obtained all these variables that was previously written in the Taylor series, which is this, and our x naught has been given to be 4. Our x naught is 4. So we are going to rewrite this whole equation, inserting this to have the general form in order to solve any problem that may come after. So we are going to have that our y, let me write it down here. Let me write it down here so that we can have that our y of x is equals to y of x naught is 4 plus x minus 4. Y prime of x naught will be replaced with 0.05 plus, here now, x minus 4 squared. Y prime prime will be replaced with this minus 0.029596 plus x minus 4 cube will be replaced with this, which is this expression, 0.023326. But don't forget, I have 2 factorial here, so let's not forget to write 2 factorial, and this one 3 factorial. So from this particular solution, we can now find our y of 4, which they said we should find, and our y of 4.2. So here is our x value. We are going to replace it here. Then we are going to find the first solution for this. Then the second one is 4.2. We are going to replace it, meaning that we are going to have 2 solutions with respect to y of 4 and y of 4.2. So let's do that quickly. Now, to obtain y of 4, which is the first one, so here we are going to replace, anywhere we see x, we replace by 4 in this problem. Let's see what we are going to obtain. So from the general solution we have obtained, after we have solved for all these variables, you have that 4 plus our x is 4. So it becomes 4 minus 4, absolutely, which is 0. So also here is 0, also here is 0. So I will not waste much time to do this, because this is 4 minus 4 is 0 times this is 0. Every other thing here becomes 0. Everything here becomes 0, because 4 minus 4 is 0. 4 minus 4 is 0. Anything over 0, we multiply by anything is 0. 0 over any number is still 0. So all this is reduced to 0. Then you see that y of 4 is equal to 4. And it tallies with the first condition that was given to us, that at y equals to 4 is equal to 4. Y of x is equals to 4, and x equals to 4, y is equals to 4. So you see it tallies with the initial condition. So next is to solve when y of x is 4.2. When y of x is 4.2. So let me give us a very short cut. Since we know that our x is 4.2 and the difference of x minus 4 with this is 0.2. So instead of writing 4.2 minus 4 to be very cumbersome, just replace it by the difference of 4 and 4.2 and 4. This 4.2 is this x. So if we replace it, the difference here will be 0.2. So we're going to replace that by 0.2 with the difference of x minus 4. So if we do our substitution carefully, we are going to obtain